So, the theorem. So let's just focus on the mean value theorem here today. First off, for the homework, that's what that was about. So the mean value theorem was this one, which basically said the slope. The key was between the endpoints. That's two of our theorems that really focus on the endpoints, right? The intermediate value theorem said that, you're going to hit all the y values between the two endpoints, f of a and f of b. That's common sense. That's what it says. Obviously, you have to say it more like this when you state it, but when you're quoting it or using it or, kind of reasoning with it, you can kind of think of it that way. But anyway, it talks about the endpoints. And then this same thing, the slope between the endpoints. If it's smooth, which means differentiable everywhere between A and B, and it also has to be continuous on the whole interval, which means including at the endpoints, has to be both those. But if we have that, then somewhere, so if I average 65 mile an hour, some point between here and Grand Island, I had to have been going 65. So the exact slope, so it connects F with F prime in kind of an equation sort of way, which is nice. Okay, so anyway, so you had to go through here. A little bit at the beginning, it talked about the converse. So if P then Q, then the converse was if Q then P. You just switch those around. We wanted you to switch that and decide if its statement is true and its converse is true, because not necessarily does that always work, right? Like we just said, if you get an A in calculus, then I'll buy you a car. The converse of that would, if I bought you the car, then you got an A. And we said that's not necessarily true, right? The promise is, if you get an A, then I'll buy you a car. What happens if you don't get an A? Maybe you get a car, maybe you don't. Now, we assume in our head that it's the other way around. We assume that it worked both ways. If you get an A, then I'll get a car. If I don't get an A, I'm not getting a car, right? So if that was the case, if that was actually the promise, then the converse would be true. If I get an A, then I get a car. If I got the car, then I got the A, right? Because that's the only way I was going to get the car, okay? But ordinarily, the converse does not necessarily have to be true. Well, let me give you these simple examples. And again, this goes back to geometry. You probably remember doing a lot of that, but that's been a while ago for some of you. So, if a triangle has exactly two equal sides, then it's isosceles. If a triangle is isosceles, does it have exactly two equal sides? Right? Because isosceles is at least two equal sides, right? So an equilateral triangle could be considered isosceles as long as it has two. Sometimes that depends on the textbook too. Sometimes different textbooks will define that differently. But anyway, here we go. If it's raining, then it's cloudy. True or false? Yeah, we could probably argue that, right? We've all been sitting out, you've all been outside in the summer and the sun's out and there's this one cloud over you and it's raining. And so, so is it cloudy if there's one cloud in the sky? Well, I think that's cloudy. So we could probably argue that. If it's cloudy, then it's raining. Clearly that's not false. If f prime of 1 is 0, then f has a local min at 1. Is that true? I'm more interested in the math ones. If f prime of 1 equals 0, then f has a local min at 1. Is that true? No. It could be a max. It could be a flat spot. Right? Go the other way. If f has a local max, if f has a local min at 1, then f prime is 0. Okay, I'll go with true, but what assumption are you making? That it's differentiable, right? So let's talk about this, because this could definitely come up in the quiz tomorrow, because one of the things I'm getting at is the concepts of, the things we've learned before, but what's been in this chapter. But then, of course, this chapter is applications of the derivative, which means it really kind of is about everything, in a sense, that we've learned. So one of the things you're going to be asked on this quiz is some true-false type questions, probably, right? Some shorter answers, some true-false, something like this. Okay, so let's just do that statement again. If f has a local min at 1, then f prime at 1 is 0. And so John's saying it has to be differentiable. What did we just say differentiable means? The derivative exists everywhere. Okay, look at this point right here. What if that was at 1? Is that a local minimum? That's a local min. So what did I just say? I said if f has a local min at 1, then f prime is 0. Is that true? That's false, right? Who won? Somebody won. They said that Ryan will be here. Should be late. Okay. Somebody was
tempted just to go home.
They were confident. If f prime is, so if f has a local min, then f prime is 0. That's a false statement unless in the directions it said f is differentiable, right? Because right there the derivative does not exist. Okay, so it's possible. Remember, that was the whole point of when we checked optimization problems, right? Why did we check? Where did we check for max and mins? When the derivative is 0, when the derivative is undefined, and at the endpoints. It was for that case right there. That's why we're checking for where the derivative is undefined. Because there could be a minimum there, right? So, say it again. So if the statement is, if f has a local min at 1, then f prime at 1 is 0, is a false statement just on its face. But if I tell you f is differentiable in the directions, then that takes out that case right there. Then, yes, the only way to have a local minimum is to be where the derivative is 0. Because by definition, early on, we said local mins and maxes don't happen at endpoints. Okay? So if I had a graph, so we've talked about this, where if I had a graph and it goes like that, that looks like it's a local minimum, right? But we would not call that a local minimum because what do we do for local minimums? We look on both sides, right? We do a number line, we look on both sides. So just by definition, we're not going to have local minimums at endpoints, okay? So that won't happen. So those are going to be separate, okay? All right, so it's important that a question like that's really important because those are some things that I may ask you. If something might, and I might ask you one where must be true, might be true, can't be true, that kind of thing. So there, if that would have been that kind of a statement, if f prime, if f has a local min at 1, then f prime is 0, then that'd be a might be true, right? If I hadn't told you that f is differentiable, that'd be a might be true, right? Because it could be where the derivative is undefined. All right, so those are things we want to understand. Okay, if x is greater than 2, then x is greater than 1. True. Flip that around. If x is greater than 1, then x is greater than 2. That's not necessarily true. So if something's not necessarily true, if something's a might be true, if it's just a true-false question, that's false, right? That's false. Okay. So I've had people ask me that on true-false. They said, well, it might be true. Well, if it might be true, then it's false. Okay. Because it's got to be true all the time to be a true. If I win the lottery, then I'll get rich. I suppose we can assume that's a true. If I'm rich, then I won the lottery. I mean, I don't know how you would reword that, but something like that, you know. That's not necessarily true. Could just be a teacher. All right, number 5. If f prime is equal to 2x, then f is equal to x squared. True or false? Did we stop at number 5 on these? Oh, we only did the odd one. Did we just do the odd one? Yeah, that was. All right. Well, those are. So we didn't do number 2. Well, I'm glad we talked about it. That's a really good question. Why did I put the odds? All right. If f prime is 2x, then f equals x squared. False. What if it's a might be true, must be true, can't be true? Might be true, right? That's one of the antiderivatives of 2x would be x squared, but it wouldn't have to be. If f of x equals x squared, then f prime is 2x. That is true, right? That is true. All right. So those are kind of some things we could ask. Didn't really have anything about mean value theorem, but it's just good practice. It's just about theorems in general, if-then statements. 8 through 11, if f has 2 roots, or you want f to have 2 roots and 1 stationary point, is there some sort of differentiable function with these properties, or tell why none could exist? So 2 roots and 1 stationary point. That'd be easy, right? That'd just be a parabola, right? So 2 roots, 1 stationary point. 2 roots, 1 stationary point. right? 2 roots, 1 stationary point. 3 roots and 1 stationary point. Can't happen, right? It can't happen, because if it's going to cross there 3 times, it's got to turn around twice. If it's going to go through, right, and then go through again, and then go through again, and it's got to turn around twice, it's differentiable, so it's got to be smooth, so it can't jump or something like that, okay? So that can't happen. 1 root and 2 stationary points. Will that happen? Right? So, wouldn't that do it right there? 1 root, 2 stationary points, something like that. Okay? All right. So, and then 11, infinitely many roots and infinitely many stationary points. Sine curve, cosine curve, right? Fit that perfectly. Okay? All right. So, and then 19 and 33. So 19, well, let's talk about 15, 16, 17, 18. Because those are about that satisfying the hypothesis and stuff. So I wanted to talk about those. If you have the absolute value function, okay, so the V graph, okay, so does that satisfy the hypothesis of the mean value theorem from -1 to 2? Yes or no? Does that satisfy the hypothesis of the mean value? What's the hypothesis? What's the if part? First part. Is it differentiable? No. It's not differentiable. So it does not satisfy the hypothesis. Okay? So it does not satisfy the hypothesis for there. Does F satisfy the conclusion on that part? We might get lucky, right? It might satisfy the conclusion even though it didn't satisfy the hypothesis. Well, what's the conclusion? It says that the slope between the endpoints, somewhere there's got to be a point that has that slope. Is there? No, so we don't get lucky, right? Sometimes you get lucky, right? Back here, right here. This one we got lucky, right? So between here and here, it is not differentiable. But if you look at the endpoints, oops, ignore that. My thing's going crazy on that. There is a place that has that slope, so we get lucky. But there was certainly not guaranteed to be a place that there would be that slope. Okay? So we get lucky sometimes on those things. But this one we don't. 17. If you just look from 1 to 2, does it satisfy that hypothesis? Sure, from 1 to 2 it's differentiable. Derivative exists everywhere. And does it satisfy the conclusion? Well, it better. Right? If it satisfies the hypothesis, it has to say, if you get A, you got to get the car. Right? Or else the thing's a broken promise and the theorem doesn't work. But the theorem does work. So we have, so if it satisfies the hypothesis, certainly. Because what's the slope between the endpoints? 1. Is there any point in between there where the slope is 1? Yeah, all of them. Right? All of them. So it definitely does. All right. So 19 would be an example of a problem that I might just have you work out for the mean value theorem. And all that is when it says explain why there must be a point, you should say something about that as a polynomial function, and it is always differentiable. That function is differentiable. So it does meet the hypothesis. So if you're going to talk about a theorem, you've got to say that it meets the hypothesis, okay, which this would. So therefore, the slope between the endpoints. So we just simply do f of 1 minus f of -1. Now show your work on something like this, okay? So if this is on the quiz, you want to show your work on something like this. So you plug a 1 in here, you get, 2, put a -1 in there. I think I'm doing this right. Okay. 4 over 2, you get 2. So I just did the slope between the 2 endpoints, so show your work, okay? Show your work on something like that. I just showed that the slope between the endpoints is 2, so therefore, according to mean value theorem, there has to be some point that has the slope of 2, okay? If I wouldn't have got 2, that would have been a problem, especially when that's working, because it sounds like it's supposed to work, right? So, but show your work. So the slope between the 2 endpoints is 2, so there has to be some point that is 2. Okay, and then finally 33, this was the one where this is kind of like we were talking about driving to Grand Island. So the toll booth, I don't know if they really do this, you know, I always think about this when I go down to the Kansas relays. and track. Go down into Kansas and get the interstate. They've got these toll booths. You got to, depending which way you go down there, and you go through and you get a ticket, right? The ticket's punched, and it's got the place that you entered the interstate and the time. And then when you get off, they take that ticket and they charge you so much for how far you went, right? And they do that so they don't have to, they use that to pay for upkeep on the roads and stuff. So they can keep taxes down. I mean, that's the idea. They said, why not just charge the people who are actually using the road to help pay for this, right? So that's the idea, right? So that people that are just passing through Kansas have to pay a little bit of money. So that's their idea on these roads. And so you can just imagine, the situation that they talk about. They say you pull off, so you're there at 1, you pull off at 2:15, and what is it, 100 miles down the road? So you went 100 miles in 75 minutes at 1.25 hours? What's 100 divided by 1.25? Then 80? So what do they know? If you just went 100 miles in an hour and a quarter, then you had to been averaging 80 mile an hour, right? So so the toll booth operator hands you your bill for, the thing, and then hands you a speeding ticket at the same time. I don't think that really happens, to be honest. If you've seen some of the people running these toll booths, I don't think they're in charge of calculating miles per hour. But anyway, I should say that. But so anyway, they hand you the ticket and they say, here you go. At some point, you can just hear this toll booth operator quoting, right, the mean value theorem. Sorry, but according to the mean value theorem, there had to be some point in time where you were going 80 mile an hour. All right, and so then you can calculate the fine, whatever, for going 15 mile an hour. All right, anyway. So if you turn in your book, well, that same page, 288, okay, there's a little bit of a summary kind of what the main points are in here. So let me go through this. So we talked about some of the questions you might, this is not one of those quizzes that's real easy to study for. Obviously, there's a couple things that are easy to study for, like the 3 theorems. You have to state the 3 theorems. So that's something you clearly can recite to yourself and make sure you get that memorized. And I may not put them in the right order, right? Make sure you know which theorem goes with which name. The extreme value theorem obviously has to do with max and mins. Intermediate value theorem, intermediate between, right? We said so. You have to hit all the y. If it's continuous, it has to hit all the y values between the 2 endpoints, f of a and f of b. And then the mean value theorem. Now, what is that about? Well, average, really. We just talked about it. If you average 80 mile an hour for the whole trip, at some point you had been going 80 mile an hour. So really, the word mean here is for average, because that's what slope between 2 points is average rate of change. Okay, and so that's where the word mean value comes from in math. Okay, so if you look on page 288, so let's just talk about some of the other things that were in chapter 4. So slope fields, probably not going to be anything to do with, we did slope fields and differential equations, stuff like that. Really, probably not going to be anything to do with that. Limit, L'Hopital's rule, we've done quizzes on that and those kind of things, and so not going to really be anything on that. Optimization, so we were talking about that. We were talking about knowing where do you look for a max or min. The 3 places, derivative 0, derivative 5, influence, that kind of thing. So just to answer your question about the process, we kind of have the recipe, of steps. Not that you have to memorize those steps or anything, but maybe be able to talk about the process of that. Or maybe I give you an example of a situation and I forgot to check the endpoints, and you have to look at it and see that you didn't check the endpoints or something like that. What's wrong with this? Or, something about the process, that kind of thing. Okay? Some definitions, possibly like critical points. Critical points is where what? The derivative is 0 or the derivative undefined. Stationary points where the derivative is 0. Right? Critical point is where the derivative is 0 or derivative is undefined. So maybe you have to define those terms or know those terms. Or the the difference, describe the difference between a local max min and a global max min, or an absolute max min, that kind of thing. Parametric, not really anything on that. Related rates, not really anything on that. That was, a lot of calculating and doing that kind of stuff in there. That next section, linear quadratic approximation, we didn't do that section. Newton's method, be able to describe Newton's method, right? We're trying to find a root. So we guess, we see if that's a root, we ride the tangent line. Now what does that mean, ride the tangent line? It means we're going to solve the tangent line to where it crosses the x-axis, and then we're going to do it again. I mean, that's the process of what Newton's method. There's the formula of Newton's method, and maybe that'd be good to know, I suppose, but I don't know that I'm that interested in that. My next guess, so if I want you to describe how Newton's method works, I don't want you to give me this formula. That doesn't describe how it works. That formula came from setting the tangent line equal to 0. We set the tangent line equal to 0. If you remember, it was y equals the derivative times our next guess, and then plus our y value. And what we did is we set that equal to 0 and we solved for this x right here. That's where this formula came from. Okay, so we want to see where the tangent line crosses, then that's our next guess, see where it crosses, that's our next guess, see where it crosses, and we circle it. Also, what were some of the things that caused problems? Well, maybe a shallow tangent root that shoots you way out there. Okay, or maybe you cycle back and forth. You go here, takes you to there, takes you back, and you just keep cycling around. That was a problem of what could happen with Newton's method, right? So those couple things, but you're not going to have to, work out a table or anything, do any calculating, right? It's all in the calculator. So understand how Newton's method works. Continuous and differentiable, okay, understand the difference there. We talked about that. Continuous, connected, no jumps, breaks, gaps. Talked about how the limit has to exist and the function has to exist, and those two have to be the same to be continuous. Differentiable adds another piece to it. The derivative also has to exist. So now you can't have any sharp points. It has to be smooth and connected. Both, right? To be able to describe the differences between those, or be able to just describe what differentiable means, what continuous means. Differentiability implies continuity, just means if you know a function is differentiable everywhere, then it's also continuous. Okay? So if it's differentiable, you know for sure it's connected. It's continuous. Okay? So that's pretty much it. I think that's a pretty good summary of the things that are in chapter 4. So we talked about some true false kinds of things. Some of those homework problems you did on extreme value theorem, maybe in 4.8, might look at that again, does the conclusion hold, does the hypothesis conclusion in the 4.8 homework. You want to look at that. Okay? So I want to do a few problems here. So now thinking about midterm, so we got that, so I'll give you some work time here, and so you could be reviewing some of that if you need to. With that time that's left, but here for a little bit, let's talk about midterm. Okay, so I've got some problems up here I want you to try. Okay, you can kind of work with each other here a little bit.
Does it give us the answer if you scan it with our
It might actually. It actually might. I bought this from there's an online site called Teacher Pay Teacher, where teachers can upload their own activities, and this was like 75 cents. I don't know that.
doesn't work when you're blocking half of it.
I know, that's why. Well, I wasn't blogging it for this.
That's your first way, you scan it with your camera and have it for smooth. Oh. Yeah, it wasn't coming up when I was doing it.
Let's consider this a calculator question. I still know that makes it easier. Does this sound vaguely familiar that we talked about how this inverse thing? Think of square root and square root of x. Square x squared and square root of x. The 0.39 is on x squared. The 0.93 is on square root of x. They're inverse functions. Oh yeah, I guess I was getting it. I didn't even know. It was giving me the answer. I didn't even know.
I agree.
Okay, so let's not waste a lot of time here. Not that it's a waste of time if you're thinking, but so I see some of you typing stuff in your calculator. What are you typing in? Jace?
I was just winging it, so I thought for the inverse I did X up there.
Nope.
It's not clear.
Anybody else? Here's why. A first thought to doing an inverse would be interchange the x and y, right? So you get y equals x cubed plus x, because that could certainly work. So you'd have x equals y cubed plus y. And then, but then the move is to solve for, well, might be the move would be to solve for y. And you can't on this one. So that's kind of why this one's picked. Okay? Now, if this is f though, if this is that y, then h is this y. Right? So you could do an implicit differentiation right now. You can't solve for y, but the only reason we would solve for y is so we could then do y prime, right? But you don't have to solve for y to do y prime. Correct? Now, there's still going to be one other thing we have to do, and that was the part that you really need your calculator for, because right now we can do the derivative here and get 3y squared y prime plus y prime. Okay? Now we want to get what y prime is, right? So we could factor out a y prime on this side, and we'd have 3y squared plus 1, and over here we'd have 1. And so we'd have y prime equals 1 over 3y squared plus 1. Now what do we put in for that y? Do you put in a 10? No. And where did you get the 10? You plug this 2 in for this x, which is 8 plus 2, which is 10. Why can't we do that? Because this 2 is the x in which function? In this function. Right? You've got to put this 2 right there and figure out what that y is. But that's where the calculator comes in. So go ahead and do it. So do a solve on 2 equals y cubed. Go ahead and try it, see what you get. Because this 2, that's what I was getting at with the interchange the x and the y. See, this 2 is the x in the inverse function, means it has to be the y in the original function. And that's the part most people miss. What do you got?
1.
1. So now you put a 1 in here, and you get 1/4. So the slope would be 1/4. Now, what I was doing with the scanner, I thought with the new operating system, I thought you can just take your regular camera and scan codes automatically. So what was happening is when I scanned it, a little thing popped up that said search in Safari, and it was searching 1/4. It searched 1/4 on the internet. I'm like, well, that's not right. I thought it was going to take me to a website and show me the solution. It just came up 1/4. This barcode just came up 1/4. Anyway, but that's what it is. Now, you wouldn't have had to done, though, the implicit differentiation, right? You wouldn't have had to done that. If you just realize it, okay, and that's what I was getting at with the 3,9 and the 9,3, the interchange. This is the inverse function. The input is 2. That means on the original, the output had to be 2. So all we really needed to do was put a 2 in here, set this equal to 2, get that x is 1. And then remember that, and then you could remember that inverse functions have reciprocal slopes. Not opposite reciprocal, but reciprocal slopes. Okay? And so then you could have just said, well, when the output is 2, this is 1, so let's find the slope here at 1. So I could have done 3x squared plus 1 right here, plugged in a 1, that would have given me 4. So the slope on this one at 1 would have been 4, so that means the slope on this one at 2, the flipped point, would have been the reciprocal 1/4, so I could have got that. I actually like this better, to be honest with you. I didn't think about doing that until you said interchange the x and the y. I usually don't do that because I know I can't solve this for y, but if you interchange the x and y, then just do it implicit. That works well too. The problem is you got to make sure what you plug in for y there is not what you got for the y here, right? What you plug in for y here, this 2 has to go in for the y there. So what the x was on this one is the y on this one. Okay? So and that always comes up, and that's why I think it's important in the midterm. So we may do another one of those this week. Those are the kinds of problems we never hardly see, but then they show up on the final. We see it like one time, and then it comes it shows up in there. So, all right, let's do another one. One that's a little more common type of problem. I got a couple of them here. So let's try this one. Okay. This one should be a little more doable. Anybody get 2/3?
Yeah.
2/3? That's wrong. So a common thing for people to do is, where does it start? Plug in a 0. Where does it start? Plug in a 0, you get 2. Plug in a 2. When it stops, 2 2/3. So how far to travel? 2/3. The answer 2/3 would be correct for what question? Displacement. Net distance traveled. Started at 2, ended at 2/3. That's displacement. How far did it travel? We got to check to see if it turned around. Did it go straight from 2 to 2 2/3? And how do you check to see if it turned around? Velocity, derivative, set it equal to 0. So you do the derivative, you set it equal to 0, you see it was 0 at 1 and -3, you throw out the -3, so at 1 it turned around. So now that's kind of like a list of candidates. Now I did a number line which was really unnecessary. I did a number line as a double check. But what I need, so it's really, again, we talked about this, it's kind of a list of candidates in a way. We took the endpoints, plugged them into the original, but also where the derivative is 0, which that's its turnaround point. So it turns around at 1, so I put a 1 into the original to see where it was, and it was at 1/3. So that means it must have started at 2, it went this way to 1/3, which is 1 2/3 distance, and then it went from 1/3 to 2 2/3. And so that's 2 1/3. So it went 1 2/3 this way plus 2 1/3 this way for a total of 4 meters. So if you, yeah, all right. So, and then I did a number line, and that's what it said, right? Negative to positive. So that just verified for me. Yeah, okay, I must have done it right. It went left, then it went right, and so total distance traveled. Okay. Now we're going to have an easier way. Now you're still going to have to understand that's what you do when we get into integrals. One of the things we'll do with integrals, there'll be several things we'll do where the integral will help us to do something we already kind of know how to do, but in a simpler way or just a more direct way. So we'll have a way to get that total distance traveled with an integral later on. But again, that's still an okay way to do it, and that may be on the quiz or on the midterm. All right, let's do one more. Try it out. Find the equations of the 2 tangent lines to this curve that have a slope of 4. Now those last couple, those would have been no calculator problems. This one and the one before would have been no calculator problems. The first one would have been just because you'd have had to have a calculator to solve that. All right, so so first you got to figure out where the slope happened, right? Where did it have a slope before? What'd you get for that? Plus or minus 1, right? So you're just going to do the derivative. We kind of went from hard to easy here today, but do the derivative, set it equal to 4. So where is the slope 4? So that'd be plus or minus 1. So what points are those? Plug your 1 and negative 1 back into this. Right? Put a 1 in there, you get 2. Put a negative 1 in there, you get negative 2. I think I did that right. And then, so now you got slope 4. So what do you need? You need to point the slope. So put your slope there, put your point there. So those would be your two tangent lines. Okay? So those are kind of some, when it gets to the free response especially, those are some of the bigger ideas that you sometimes run into, position, velocity, acceleration kind of questions, tangent line kind of stuff, but that also can show up in the multiple choice for sure. All right, just a couple more things here. This is the 2012 free response. Let's look at 4C here. Since we've been talking about continuous functions, I thought that would apply here. So let's review that real quick. Try 4C. Yes or no?
Yes.
What'd you do? Plug negative 3 where? Into this. What do you get? 4. And into this, 4. That's it. That's all you need to be continuous. Okay? Now, let's add one more piece to this, which they didn't ask, but what they could ask is it differentiable? And that's kind of a new question for us, but since we've been talking about differentiable, now this could show up. Is it differentiable there? So, if you've got a piecewise function, I got to stay plugged in here, so if you've got a piecewise function and you want to know if it's continuous, you need to know when the one graph stops and the other one starts, that they stop and start at the same place, right? So that's what you did there. You put negative 3 into both pieces, see if they start and stop at the same place. They did at 4. Now, to be differentiable, what has to happen? The slopes have to be the same. It has to be smooth. The transition not only has to be connected, it has to be smooth. Okay? Now, I will go ahead and show you here what I did. Now, this would be enough to finish. We'll finish the problem here in a minute. But what's going to happen is, hopefully you recognize, maybe not, but this is the top half of a circle. That's negative 5 and 5, okay? Because if you square both sides, you have y squared, then you have x squared plus y squared equals 0.5. That's a circle at the origin, radius 5. So this is the top half of that circle. So it's going to come around, it's going to be that circle from negative 5 to negative 3, and this is going to take off and be this line with a slope of 1 and a y-intercept of 7. Well, it's going to be a sharp point, okay? It looks to me like, at least in my picture, now maybe my picture's wrong, I don't know, but I guess what I should say is, because I haven't shown it yet, it looks like it could be a sharp point, right? That's not differentiable. It has to be a smooth transition to be differentiable. So, if they ask you, is it differentiable, that's like asking two questions. It has to be connected and it has to be smooth. So you first do what we did. So you first would check, so if the question was, is it differentiable at x equals -3, you would see, well, is it continuous? Are they connected? So you plug -3 in, yep, it's connected, they're both 4. Now what would we have to do? Are their slopes the same? Well, what's the slope on this one? 1. How do we get the slope on this one? Do the derivative. So we'd have 25 minus x squared to the 1/2, so that'd be 1/2, 25 minus x squared to the -1/2, times the derivative of the inside, which is -2x. So let's do that. So I'm going to flip that down to the bottom. I'd have -2x on top. I'd have a 2. I'd have a square root of 25 minus x squared. Okay, I could cancel the 2's. Now let's put a -3 in there. So you put a -3 into here, you get 9. 25 minus 9 is 16. Square root of 16 is 4. Put a -3 there. That'd be +3. We get 3/4. So is it differentiable? No. Okay, close, but the slope here is 3/4, so it's less, and then it switches right away to a slope of 1. And so it's not differentiable. So that is a question that they could have easily asked that we may be responsible for. Okay, so piecewise function, continuous means they're connected, differentiable connected, but also smooth in the transition. Okay, yeah, I'm going to let you work. We can do some work tomorrow, or the next day, Wednesday and Thursday. All right, so for tomorrow, I think you need to work on that exam 2, probably. I don't know if everybody took one the other day, because I still have a stack of them here. So the next thing we should be working on is the exam 2 packet, because you're going to get exam 3 probably Wednesday. So we want to be working on that obviously getting ready for the quiz tomorrow, finishing the take home, but exam 2, get going in that. That's the third packet, okay? So if you already took the third, what we have for packets is sample 1, sample 2, those were the first 2, and then we're going to have exam 2 and exam 3. So if you already took exam 2, that's the one I'm talking about. Nobody's taken the 4th packet yet, I don't think, okay? Which is fine, we'll probably give those out on Wednesday.
You make sure you take out all of it.